So today we're pleased to have Yuri Levin here. I'm going to quote from Yuri's webpage at the Columbia Physics Department, which says that he got his PhD at Caltech and then went traveling around the world before landing as a faculty member at Columbia University uptown. And he's here to tell us about resonant friction in disks in galactic nuclei.
Okay.
Thank you.
So thanks very much. Mike warned me that there might be some particle physicists in this talk, no particle physicists. Because I prepared, I decided to put this movie in. This is the movie of stars. I mean, astronomers have seen this movie, but this is the movie of stars going around the black hole at the center of the galaxy. And the 2020 Nobel Prize, at least half of it went to the two researchers who have made these maps, made these movies, thus measuring very precisely the mass of the black hole, unraveling the interesting stellar dynamics at the center of the galaxy, which is partly what I'm talking about today. So what is my plan? So I want to talk about extreme mass ratio in spirals, which emerges of small black holes with supermassive black holes in the centers of galaxies. And I will mention two types of in spirals, two types of laser signals. Then the main part of the talk is a disrupted young stellar disk near Sagittarius A star, and I hope to convince you that perhaps resonant friction solves the puzzle about this disk, which has existed since its discovery in 2003, and hopefully also tells us something about how the nucleus works. Then I will mention the connection between resonant friction and thermodynamics of the stellar clusters, and then I'll end with speculation of how friction acts on accretion disks and whether or not it has impact on spins of supermassive black holes. We already discussed this morning at the reading of the archive that there is some apparent tension with the results from PhD here. Okay, so just to start very broadly, what is known about supermassive black holes? Supermassive black holes are massive black holes in the centers of galaxies. They have masses between, let's say 100,000, and the most massive supermassive black hole currently known is quoted to be 6 × 10⁻⁻10 solar masses. We know for sure that they grow they acquire most of their mass by accreting gas from thin disks, so it's a very specific way of accreting gas. This is so-called famous Dalton's argument. We also know that majority of supermassive black holes are now dormant. So if you look at galaxies nearby, are all nuclei, Andromeda galaxies in the local group. The nuclei of these galaxies are basically not active. You need to look much further out to start seeing AGNs. So most of the black holes that we see around us have stopped accreting gas in industrial quantities. They accrete a little bit of gas, but not enough to substantially grow in their mass. Okay. Then we also see that many of these black holes are inside nuclear star clusters, not nuclear physics, but nucleus of the galaxy, right? This is where nuclear comes from. If you look at the Milky Way here, this is a central 5 parsecs of the Milky Way. Sorry, the circle has a radius of 5 parsecs. You see inside the circle there is a concentration of stars. This is a nuclear star cluster around Sagittarius A star is inside this cluster. This is a zoomed in version, and where you can actually see that you can resolve individual bright stars inside these clusters. Not solar type stars, unfortunately, on the main sequence, but when the sun when solar type star becomes a giant, and you can see it, or if the star is very massive and produces a lot of radiation, a lot of luminosity, a lot of radiation, you can also see. Some individual measurements for the stars. And Andromeda has a very different nuclear disk. So this is what it looks like, and it looks like two nuclear star clusters. In fact, this is an optical illusion. It's a mirage. So Tremaine has explained, and this explanation now has been abundantly confirmed by extra tests, is that in fact what we are seeing is a black hole is sitting inside this dimmer concentration, and the brighter the stars are moving around this black hole on this eccentric disk. And the reason why you are seeing the second blob is because the stars are moving slowly near the upper center, and so there is more chance to observe them. So there's a concentrated traffic jam basically at the upper center of this eccentric disk. So the traffic jam is this thing here. Okay, so very interesting morphology. These are the two obviously nearest to us nuclei of
And if you go to larger scales, will you see that the black hole is in the center of the bulge or whatever?
Yeah, so the black holes are...
So people were never confused that second nucleus is the true center.
Oh no, they were. They were. It's not that well centered. I don't think.
Okay, so you cannot center it.
You cannot center it like that. Yeah, the distance here between the two concentrations, I think, is 2 parsecs, which is much smaller than the size of,
Of the bulge.
Yes. Okay. So this is phenomenology that I want to tell you. Okay. Now about extreme mass ratio in spiral. So these supermassive black holes, one of the most interesting things about them is that we expect them to merge with small black holes around them. So this is schematically shown here. Let's say 10 to the 6 solar mass black hole merging with a common stellar mass, let's say 10 solar mass black holes, giving gravitational waves. This is one of the primary target sources for LISA, which is a satellite which is expected to fly in mid 2030s. So I really hope that I'm still alive in that time. And these waveforms that will come from these mergers are very, very interesting because, first of all, this type of waveform carries information about space-time. So, in fact, there is a theorem, mathematical theorem proved by Fint and Ryan, that information about all multiples of space-time, all multiple structures of space-time is uniquely contained in such a waveform. So, if you measure it with infinite precision, you can obtain a complete map of the space-time of the central object, and in particular, finally, Roy Kerr can get his Nobel Prize because currently we don't have direct information that the metric around supermassive black holes is Kerr-metric. We all believe it, but there is no experimental confirmation.
But is not the very merger and the resulting signal based on Kerr-metric?
Oh, you can. This statement that this is this would carry, whatever space-time you have, information about the space-time would be contained in the waveform.
But we have measured already gravitational waves, right?
But we have no
If Kerr was a wrong metric, the numerical simulations of merging black holes leave behind exactly Kerr.
We don't know that.
What are you talking about?
There is no evidence of that.
But if, in their computer, they see Kerr.
They don't.
After the black holes have merged?
The computer, yes, but the observations, no.
But if the left behind was different from Kerr, the outgoing train of gravitational waves will also be different.
We don't have this type of precision, this measurements.
Is it a problem of not seeing into the high frequency after?
Yeah, you only see, it's very rough. You see basically, several cycles. You hardly see them in.
So you are saying you can notice it.
But they greatly constrain the spin of the incoming black holes, right?
The incoming black holes, yes, from the inspiraling
But
signal.
this means that they do have Kerr-metric.
They have some gravito-magnetic component, but can be something else.
It could be some other post-Newtonian.
Gravito-magnetic component, yes, but the spin measurements are very imprecise.
But still, there is curve.
There is a hint of curve. There is a hint of curve-like things, but in terms of precision measurement, it's actually curve and not something else. We don't have this evidence.
I don't understand this at all. The calculations of this highly sophisticated gravitational wave train
Yes.
are based on GR.
Yes.
GR leaves behind curve metric, which
Yes.
they see in the same simulation from which the gravitational waves came. And yet you are saying we don't have a confirmation of. Okay, this is getting too philosophical. Yeah.
Okay. So there are two ideas for how, two theoretical ideas for how you can get, such mergers. So the first idea is that you can, because these small black holes live in a cluster around the big black hole, the orbit evolves stochastically, and occasionally a small black hole will get into a radial orbit which passes very close to the big black hole. When it does so, it emits a train of gravitational waves. This is gravitational wave Bremsstrahlung. And so this would capture small black hole in a bound orbit, and through repeated emission of these gravitational waves, finally the orbit would shrink and merge with the big black hole. And so it's obvious that the signal from such a merger would be highly eccentric in spiral, which is oriented randomly relative to the spin of the black hole. Okay. There is a second idea which I worked on in early 2000s and some other people as well, is that some of these black holes, most of them do not, but some of these black holes, they have this accretion disks. And then I've argued that you can actually, this accretion disk can give birth to little black holes inside them. And then these little black holes can migrate through type 1 migration through the disk and merge with the big black hole. And so this would give a very different signal, right? Because of Bardeen-Peterson effect, these disks are expected to line up with the equatorial plane of this big black hole. And so when the small black hole merges with the big black hole, it's expected to be circular orbit in the equatorial plane. So very, very different type of signal. Much easier to look for this signal. It's quite hard actually to look for a signal which comes from this type of thing. And it's much easier to look for a signal from this type of thing. Now, in order to make this scenario in 2003, I had to think about the masses of stars which will be forming in such accretion disk. And I came to the conclusion that these masses had to be quite high. And when I was at CETA, I was talking to Norm Murray, and he said, well, do you have any observational evidence for such masses? That this type of disks give birth to high mass stars, etc.
You mean regular high mass? You mean 10 solar masses? Or what do you mean by high mass?
Tens of solar masses.
Right.
Tens of solar masses. And so this was the question. Is there any evidence that massive stars are ever born inside accretion disks? This was the question in 2003. And there was only one place to look, and I'm asking you, what is this place? Center of the galaxy, right? Because this is the only black hole that we know exists. So I went looking, and I have to say that the location of the center of the galaxies has plenty of massive stars. Okay, so if you look at the where different stars are, so this is the central 5 square parsec of the galaxy, and the spectra of massive stars and the spectra of giants, which are the individual stars that you can see, look very different. So the hot OB stars, they look like this. They have bracket gamma in absorption. Wolf-Rayet stars, which are sort of descendants of these hot OB stars, some of them, they have bracket gamma in emission.
This is all infrared stuff.
Yeah, this is all infrared.
Okay.
This is all infrared. You can see that these are microns here on the x-axis, and you see the cool giant stars. They look completely different. So even I, who doesn't know any observational astronomy, even I can see the difference between these spectra. So I can imagine that an observational astronomer just immediately. So if you take 5 central parsecs, square parsecs, and plot where the old stars are, they're all over the place. But the young, massive stars, this Wolf A and Hoto B stars, they're all concentrated within the central half parsec from the black hole. So drastically different distribution between the stars. Okay. So the question is, yes, you do have massive stars that are somehow born near the black hole. This was already known. You know, this was already known since late 90s. But the question was,
But are they massive or are they just young?
They're both. They're massive, and therefore they have to be young.
Right, but you also have to show that they're not the lower mass stars forming.
They're not the low. Well, yes. Right, you had to show this, and there is an argument. Why? The argument is that if there were lots of lower mass stars which were forming concurrently with these massive stars, young lower mass stars emit copious amounts of X-rays. They're very magnetically active. And Chandra doesn't see this. You know, if you look at this region with Chandra, you don't see emission of, from hundreds or thousands of.
You mean they're individually active? You don't mean like low mass X-ray binaries?
They're individually active,
Okay.
just from their coronae.
Oh,
If you look at young low mass stars, when they're at this stage of their life, they produce copious amounts of X-rays.
Okay.
Even they're several million years old, and you just don't see this. So that's it. This is the argument by Akshin and Sunyaev, which I think was very clean. Everybody agreed with. So anyway, so you don't see any evidence of young low mass stars, but you see evidence of young massive stars. So according to my thinking, the only thing which remains was to see if there was a disk-like structure. Okay, so this was what Andrei Belobrodov and myself set out to do, and we noticed that for some of the stars, at least in 2003, there were of course, you don't know the full three-dimensional positions of the stars, but for some of them, both radial velocity and proper motion velocity on the sky was measured. So you can check if there is a disk-like structure in the velocity space. So this is the view of stellar velocities as seen from this special plane that we found. So you can see there were 13 stars with measured three-dimensional velocity. Out of these 13 stars, 10 lined up very beautifully and statistically significantly with this plane. Now, and all of the stars were moving clockwise on the sky relative to the black hole. Their motions were pointing in a clockwise direction. There were 3 outliers, okay? Very strong outliers. So 12, 13 were actually moving in the opposite direction.
Yes? Clockwise again means against the rotation of the galaxy? Or?
No. Galaxy. This is black hole is there,
clockwise as seen from
on
Earth.
The sky from proper motion.
As seen on Earth.
Yeah, very simple-minded. Just proper motion of the stars.
And the disk is also perpendicular to the line of sight?
No.
Okay, so it is some inclination.
It is some inclination, yes.
And in this inclined, it goes clockwise.
It goes clockwise, yes. And 11th star, even though it was also going clockwise, but it was way off the plane of the disk. So 3 out of 13 stars did not belong to the disk, and 10 beautifully lined up. Okay, so there's already some, question. What about these 3 stars? What happened to them? Out of 13. So of course, people went and collected more data, and many people have looked at with substantially larger data sets. And actually, now there are not just snapshots of velocities, but there are orbits which are now obtained, full orbital solutions which have been obtained for some of the stars which are in the disk. And the orbital solutions confirm that they're in fact inside the plane of the disk. But the picture has emerged is that, let's say, about half of the stars are in the disk. So this is a picture, I think, from Jessica Lu et al. This is UCLA group. And you see this concentration of, angular momenta vectors on this plane, but there is also diffuse clouds which do not belong to this concentration. So about half of the stars are outside of this concentration. And the Germans and Americans, the Nobel laureates, okay, they've been arguing with each other for a long time whether you can actually discern a second disk-like structure here, or whether this is a diffuse cloud. The Germans believe that you can discern some other concentrations. Americans say this is not statistically significant, it's just basically diffuse mess. So there is some arguments between the two groups, what exactly is the morphology of the rest of the stuff, okay?
Did you say what's the scale on there? I can't read the fine print.
This one? Oh, this is just degrees, 0, 30. This is the sphere. This is trying to visualize the sphere. So what you do is you plot angular momenta vectors on the sphere and
Directions of angular
directions of angular momenta.
And the sphere itself is a half a kiloparsec.
No, this sphere is
Half a parsec, essentially.
This is the sphere of angles.
This is a
That's
sphere
right,
of
but
angles.
and
It doesn't have a
density
radius.
boost
But the
that
stars
they're talking
themselves-
about
The
is
stars
the
themselves
region
are
around
within the central 0.4 parsecs.
And only massive.
And only massive, yes. Very massive, OB or over here. It's about 100 of these guys. Okay, so this is the observational situation. So when we found this disk, I was very happy because it sort of confirmed my ideas on the one hand, but on the other hand, there was this kind of, I was very bothered by this, and I have remained bothered by this diffuse cloud of stars, because there is always a possibility that this scenario for how you make these massive stars and the disk, there's always a possibility that this is just wrong, something else.
But sorry, you never mentioned. So your scenario is there was a disk, and out of this disk you produced stars. The disk now disappeared. Stars stay behind.
Yes.
Okay.
So the stars are just remnants of this gaseous disk. So, and people now sort of appeal, with the Fermi bubble story, for example. One of the ideas is that this disk produce some accretion episode on the sun.
Oh, your stars are the remnant of the episode
Of
which
the episode
produced
which
Fermi
made
bubbles.
the Fermi bubbles. Yeah.
That's too romantic.
Okay. Yeah, I agree. Anyway, so this is the story. So there is this puzzle. Okay, what's happening to the disk? And I think the key to this puzzle is that the central cluster, the nuclear cluster in which this disk is embedded, is rotating. So this is the radial velocity. This is now looking at pixels, so integrated spectroscopy, right? Not at individual stars, but integrated spectroscopy. And so this is the radial velocity as a function of projected distance along the galactic plane in arcseconds from the Sagittarius A star black hole. And you can see clear signs of rotation. So it goes out on the left side, goes in on the right side. The scale of the disk corresponds to the size of this inner bin. Unfortunately, the data is not.
Okay, so the nuclear cluster is this bigger structure.
The nuclear cluster is bigger structure. It goes, its mean radius is about 5 parsecs, so 10 times as big. They say that the edge is at 8 parsecs, but the mean sort of the substantial radius, let's say, is 5 parsecs, right? So they make this, and the disks correspond to the inner, 10% of the nuclear star cluster, right? And so these are the line of sight velocity maps. This is the data that they use to obtain, plots like this. You see, it's a little bit noisy. So anyway, this is what it is. And now I showed with numerical experiments that if you
Sorry, can you give some interpret? So the nuclear star cluster, so your stars are rotating in a disk which is inclined relative to our line of sight. What about the nuclear star cluster? Is it rotating along the galaxy?
along the galaxy.
So, as expected, so to speak. Well, whatever
This is the
it is.
fact. We don't know.
We don't know what is expected.
We don't know what's expected, but this is the fact.
But this guy is aligned with the
This
galaxy.
guy is aligned with the
unlike
galaxy.
your disk.
Unlike the disk. Yes.
Okay.
This guy is aligned with the galaxy. So, but I think this rotation is really gives a clue to what happens. So all you have to do is you have to, I mean, once it's sort of crystallized, it's clear that what you have to do, you have to start, a simulation of a disk which is perfectly aligned, but inject it into a rotating nuclear star cluster and not into a nuclear star cluster which is not rotating. So it's this rotation which makes a difference. And I will demonstrate this using simulations. Yes, Mike?
No, I will wait for your demonstration.
Okay.
I'll see if I have a question.
So I start here with 100 stars, right? And what I do is that, I plot the unit vectors to the orbital planes of those 100 stars. And and I plotted the z component. Somehow it got cut out, but this is the z component of the unit vector, right? Z being the axis perpendicular to the galaxy. So nz means nz equals 1 means that all the stars are in the plane of the galaxy going in the same direction as the galaxy, okay? So I inject the cluster in the opposite direction with which I inject the disk in the opposite direction with which the cluster is rotating, and I'm marking with red.
Is it the actual direction of your disk stars?
Yes.
So this is the actual like.
No. I inject, not in the actual.
Well, this
direction.
is what it used to be.
This is what it used to be. Let's say.
Supposedly.
Supposedly,
Okay.
yes. For example, I'm just giving you what the type of things that happens, right? If you inject the disk in some counter rotation to the cluster, okay? And what I see, if there is no rotation, if I set rotation rate of the cluster to be 0, then the disk does not dissolve. This is what everybody was finding before me as well. They don't know why the disk would dissolve. The disk does not dissolve, okay? But then I gradually increase the rate of rotation of the cluster. And you see wonderful things happening. So the green ones are the inner half of the stars, and the red ones are the inner half of the stars, and the green ones are the outer half of the stars.
And this is just n-body interaction?
This is just an body.
Okay.
Now, I have to run this for millions of years. This MRS, there has to be a missing Y. This is mega years, right? Millions of years. I have hundreds of thousands of stars in my nuclear star cluster. So if I did a direct n-body, I would go crazy. So what I do is I replace the n-body, the full honest n-body calculation, which would take years to run. I replace it with a simplified Hamiltonian, which just couples orbits secularly, right? So the orbits are averaged, and they averaged, in fact, not just into ellipses, but also into annuli, because the ellipses precess. And then the annuli are replaced with circles. So there is a simplified Hamiltonian.
And it's not self-gravitating, it's just there's a point source at the center.
There is a point source
Yeah.
at the center, and all the orbits are interacting with each other.
But it's the orbits are allowed to interact.
The orbits
I
are,
see.
of course, allowed to
Okay.
interact with each
Yeah,
other. So
okay.
in this sense, it's n-body.
Yeah.
But it's just the Hamiltonian is orbit average, so you don't spend all of your time tracking elliptical orbits. Okay, so there's some cheating, no doubt some cheating, but I believe that these simulations faithfully represents the physics which is responsible for the effects that I'm demonstrating. And the effect that I'm demonstrating is that as you increase rotation, you see the inner component always goes north, okay? This is the age of the disk. The age of the disk is about 6 mega years, right? So you can see. I think the reasonable rotation rate as indicated by those observations, which are a little bit noisy. I think it's between 0.3 and 0.4. This is the estimate that I get for this rotation, dimensionless rotation rate of the cluster.
You mean this is V over sigma or something?
No, it's a little different. It's not. It's roughly V over sigma. That's not. This is some rotation parameter. Okay.
Okay.
It's not exactly V over sigma. It's a rotation parameter of the cluster. But I see a lot of interesting phenomenology. You can see that the outer ones, they know that.
What is red and blue?
Red
and yellow, or whatever is this color? Green.
Green. Red is the inner half of the stars, and green is the outer half of the stars.
So outer part is more left alone than
That's
the
right.
inner part.
That's right. And this is exactly what is seen in the phenomenology. And the outer part is more dispersed, and the inner part is more coherent. I also sometimes see that the inner part also breaks into some, pairs of rings. These are the two rings, for example, which are nested into each other. Not always, here, for example, it hasn't done it, but there are occasionally these transient rings. So it's very rich phenomenology, but it's very reminiscent to what's actually happening, in terms of what people observe. People can look at this plots and say, oh, we see a structure here. We see this, we see that. Anyway, so I think it qualifies as phenomenological success in explaining, roughly speaking, what's going on. That there is some part of the disk which remains coherent, and there is some part of the disk which remains dispersed, and there are all kinds of structures, depending on the simulation. These are randomly chosen. I did not choose them with any angle of showing interesting features. This is just I decided, okay, I do 6 simulations in a row, and then I just.
But what will be Z for the stars which are in your disk?
What will we see?
Z. What will be the Z parameter for the stars in your disk? Because you know orientation of your disk relative to our star cluster. What will be the?
Oh, it's about half.
It's plus 0.5.
It's plus. Yeah, it's plus. So you can see.
So you don't quite make it at rotation parameter 0.3, but at rotation 0.4 perhaps.
Yeah. But also my initial conditions, I started with extreme.
Right, you did not, how to say it, you did not adjust.
I did not adjust anything. I just started with some initial conditions, and let's see what type of thing happens. I'm convinced that this phenomenology is very similar to what's observed. This has never been.
So the disk which produced your stars was like what? Was not at the same orientation as it is today. It has been rotated by the interaction.
Right.
That's your interpretation.
That's right.
But it has been rotated without disruption.
But the reason you went down this path is because there are these extra stars.
Yes.
And it's those ones that you need to explain.
That's
right.
Yeah, you need to explain how come all this guys.
But simultaneously, his explanation requires that others were rotated.
Right. Yeah.
So how you keep some and not others, right? So you really need partial disruption.
But the nuclear star cluster that's driving this, whose rotation you're tracking, is much larger, and is it treated as spherical? I was confused because your other picture made it look like it might be like a blob that's orbiting itself. I'm not sure I understand what the geometry is.
It's not treated as spherical. I just give it some angular momentum. So it's not spherical, it's flattened by this angular momentum. So this rotational parameter.
Otherwise, it's axially symmetric.
This rotational parameter, so remember that I put numbers here. I'll explain what those numbers is Mike's question. But yeah, it's modeled self-consistent. There is no external. I'm not assuming any potential.
There's no specific axial structure.
It's not like Andromeda.
I'm initializing it in my simulations as axially symmetric. That's the
Consistent with observations. right?
consistent with observations. Yes. But
Because in your first slide, you simultaneously showed us and Andromeda. And
Andromeda is very different, but we are actually symmetric.
That's what I
Okay,
just
more or
wanted to
less.
show you.
At those scales, people say that at larger radius there is some asymmetry, but at those radius, radii, half parsec, it's actually symmetric. Okay, so now question, why is the heavy disk aligning with the cluster's rotation? And I'm going to argue that this is similar to the question of why if we have a jar with in gravitational field, and we have light atoms and heavy molecules in this jar, and heavy molecules they sink to the bottom of the jar, right? This is a well-known fact. And you can look at this fact in two different ways. One way is just to write down the Boltzmann distribution, that the probability of finding an object of mass m and gravitational field at some temperature is given by this, right? So if m is large, and the scale height of this distribution is going to be small. So everything, Boltzmann demands that these things concentrate at the bottom of the jar. But another way is to look at an individual molecule and ask a question, what's happening to it? What is actually bringing it all the way to the bottom of the jar? Now, and the key agent that is bringing it to the bottom of the jar is dissipation, is friction. If there was no friction, you would start the molecule somewhere, it would just keep bouncing up and down, never get to the bottom. You have to have it experience friction, which actually drives it, dissipates its potential energy and drives it to the bottom of the jar. Okay, so in some sense, these two things are related in statistical physics, and statistical equilibrium demands that there is friction in the system, right? So that the Boltzmann distribution can be observed. Okay. Now, I will argue in a second that my disk is like this heavy molecule. Okay. This heavy molecule may consist of light atoms, right? But so long as these atoms stick together, so long as they're coherently acting as one, this molecule sinks to the bottom. If you dissolve this molecule into small components, they'll diffuse back up, okay? And then there will be nothing left, okay? So it's so long as the stars in my disk contribute together coherently to the gravity of the disk will behave as a heavy molecule, and it will be very sensitive to, these heavy molecules, they're sensitive to gravity. If the gravity is pointing down, they go down. If the gravity is pointing sideways, they go sideways, okay? So the disk is very sensitive to what the cluster is doing, much more sensitive than individual stars. This is the thrust of my argument. Now, another cute thing is that we are all used to be talking about positive temperature. However, on Sager, a great physicist, theoretical physicist of mid-century, in 1949, he showed that if the phase space of a system is finite, and you can well have negative temperatures. Example, let's consider a system which consists of only two level atoms, okay, which are interacting with each other, but not with the outside world. If you put 60% of these atoms in the up state and 40% in the down state, this fraction cannot change, right? So that means that the temperature, the beta, is negative, which the beta which describes this equilibrium is negative. If you now take another atom which has 10 different levels, right, and put it in equilibrium with those atoms which are all mostly in the upper state, you'll find that that atom goes up. Okay, that atom occupies a higher energy level rather than lower energy level. So it observes Boltzmann distribution, but with negative beta. So in our normal life, this is not allowed, okay, because in our normal life, we have infinite phase space. And so if you take negative temperatures, you get divergences, right? But in stellar star clusters, you have finite phase space, and this is allowed. So you can have negative temperatures just as well as positive temperatures. Okay, so I've already explained this point. the weird thing, of course, at positive temperature, you occupy the lowest energy level, the negative temperature, you occupy the high energy level. Okay, and one other thing is that mentally it's much better to think of this beta rather than the temperature. Beta is the inverse temperature. So maximum entropy state corresponds to the beta equals 0. All right. One other thing which I have to say is that the normally, when I enter onto your floor, I see Boltzmann distribution written on the door, and this Boltzmann distribution only has this part, e to the minus beta e. So somehow angular momentum does not get equal representation in that formula. But this is wrong, in our times of social justice, I think, we should represent angular momentum just as equally as energy. It's an additive constant, the same counting argument that applies to energy has to apply to angular momentum, right? So you have the real distribution should be beta times E plus gamma vector times L vector, okay? And gamma is the rotational vector of the cluster. It is this gamma that I'm plotting in those plots, okay? This is a thermodynamic quantity which characterizes the cluster, okay? So it doesn't have a very easy VR over sigma kind of snappy thing, okay? Because it characterizes everything at all radii, just like the temperature is valid at all radii. Yes?
Couldn't the angular momentum be baked into the energy block?
Second?
Couldn't you include the angular momentum into the full energy E? You use like a Hamiltonian. You can rewrite the variables.
Yeah, you can choose any additive, any sort of additive conserved quantities which you have could be, a player in this equation. It's just that, our natural quantities are energy and angular momentum.
But are you saying that, like, if you let all this stuff interact, you will get this distribution?
That's right.
Like, that's the thermodynamic thing
That's
that
the
happens.
thermodynamic thing that happens.
Okay.
I'll explain this in a second. This is a very interesting understanding that has emerged over the last 20 years or so. That near black holes, so typically thermodynamics, statistical physics is terrible for gravitational systems. But near black holes it's good. Black hole regularizes things enough that thermodynamics becomes, and statistical physics becomes a good description, okay? And the reason is, again, in this orbit averaging. So if you don't consider, and this is really argued for the first time in Rauch and Tremaine in 1996. So what they have shown, two things, okay? The first thing is that the essential feature of interaction of particles which sit near black hole potential is not to think about like every second interaction, this particle with this one and this with this one. You really have to understand that particles move on elliptical orbits which remain stable for many orbital periods. So you can average these interactions, okay? This is one particle, this is another particle. If you look at these ellipses, you see that on average, these ellipses exert torques on each other. So the angular momentum relaxation is really fast because of this torque, this torques act coherently for many, many orbital periods. These are not just some random chance Coulomb encounters. These are the interactions which have long coherence time, long memory, and therefore, as a relaxation process, this is really fast, okay?
So just to put a fine point, if this was a self-gravitating thing, these things would be in rosettes, and you wouldn't get this effect. Okay.
Yes, exactly. And so they have argued and then implemented over the years a scheme that, in fact, this relaxation, this fast relaxation, it does lead to well-defined statistical physics distributions, okay, which are described by Boltzmann statistics. Okay, I already said all these things, and now I just want to say that some of this equilibria can be quite funny. So, for example, this data parameter, okay, like I said, it can be negative, and what Tremaine and colleagues have shown is that if you take beta, which is negative, you get spherical distributions, and then as beta increases, when it exceeds some value, you get a phase transition in those clusters, and you get lopsided distribution. So this phase transition happens that the clusters go from like spherical distributions to lopsided distributions. Okay. Now, these studies by Tremaine and colleagues were very nice studies, but they had problems, which I list here. And these problems were solved by this gentleman here, sitting at the first row. And I'm just going to show you some things that that could, well, actually, let me skip this argument, but I think I'm running out of time. So Andre has developed a very robust algorithm to obtain these equilibria distributions, and he's also included the stellar mass black holes in these distributions. And you can see the point that I was making, that black holes, they always amplify what the cluster is doing. Okay, so for example, here the cluster is slightly lopsided, so it has made a small phase transition to small lopsidedness. But black holes, you know, they're really lopsided. Okay, they really amplify it. Here, the cluster is barely rotating. You know, you have some rotation, which is edge-on rotation. But black holes inside this cluster, they form a flattened disk. Okay, so
What's different about the black holes than the stars?
they're more massive. They're 10, 20, 30 times more massive. So just like I said, heavy objects, they occupy special orbits. They go to the bottom.
It's just mass, it's a 1.4 solar mass black hole would act the same as a 1.4 solar mass.
Yeah, one solar mass black hole acts exactly the same way, but they're just more massive. So they're very sensitive to what the cluster is doing. Okay, just to illustrate, I made this what I thought was fun simulation where I just took, you know, you can program it in the computer in 1 hour. It's an n-body simulation. You take 100 stars around black hole. You take another 100 massless particles, they're test particles, and you take one heavy star, which weighs 5 times as much as the others. And what I plot here, this is the again NZ component of the heavy star. These are all the other stars, okay, and then yellow is the test particle. So okay, sorry. But the test particles are brown, the stars are blue. These are Boltzmann distributions that this thing should relax to, and this is the black hole. So it's a very simple numerical experiment, but I think, you know, all of you can demonstrate to yourselves that this works. You see that black hole really flips, and this cumulative distribution of z angular momentum of the stars, as you'll see in a second, they'll relax to the...
Sorry, I don't understand. Are you saying you have confirmed that it relaxes to Boltzmann? Or?
Yeah.
Oh, but in this simplified quartic interaction? Or...
Yeah.
Okay.
Yeah.
So you obtained Boltzmann on a computer?
Yeah. Here's just 100 stars. You can...
Why doesn't this evaporate?
Because it's all orbit averaged. So the same major axis.
So you don't have any regular relaxation.
Don't have any regular.
Okay.
But this is much faster than the regular accretion. This is
right.
the big point of Tremaine's work.
So it would evaporate over much longer
Over time, yes.
Because an ellipse cannot evaporate.
Ellipse.
Yeah.
It's a restricted dynamics with fixed semi-major axis.
I think you have forgotten to mention that ellipses keep their
semi-major axis, exactly.
That's why they cannot
this
evaporate.
This is adiabatic invariant, right, of this type of dynamics. Okay, and eccentricities, again, if you plot eccentricity, if this is the eccentricity of the background stars, this is the eccentricity of a 30 solar mass black hole, right? So it's much bigger. If the background stars is a little higher eccentricity than this 0.67. If the background stars have eccentricities which are a little bit lower, the black holes amplify and become much more circular. So black holes, what I'm trying to impart to you, black holes, heavy objects, are really sensitive thermometers to what the cluster is doing. And this is why when the disk acts as a single body, it experiences huge torque which tries to align it with the rotation of the cluster. Okay, just last couple of minutes. When do I have to stop? 3 minutes, yes?
No, 3 o'clock.
Oh, 3, okay. So I have more than last couple of minutes. Okay, well, this is now a speculation, but if you have this type of thing acting on the fossil of an accretion disk, what I believe is the fossil of an accretion disk, presumably if accretion disk was longer lived, this would also act on an accretion disk itself, right? And so here, I just draw a cartoon. This is a pure speculation. Please don't, I'm not proving anything, but it's a concept, right? If you have a rotating cluster and you have a molecular cloud or a cloud of gas which fell in, and this is how we think some black holes are fed. We think that some black holes are fed stochastically by infalls of this gaseous material. So this cloud fell in, got tidally disrupted, formed a disk, accretion disk. If the angular momentum of the accretion disk is misaligned with the rotation of the cluster, the same thing should happen, right? As happened to the stellar disk. You should have this interaction, okay? This disk will distort the cluster in such a way that the cluster will torque the disk and bring, torque the disk towards co-rotation. And then the final state should be that the disk and the cluster are rotating together, okay? So this is why I'm saying there is some tension between this conceptual picture and the results from EHT, because EHT says that Sagittarius A star is not rotating in the same direction, the same spin axis as the cluster. No, it says that Sagittarius A star spin is pointing more like towards us, or it's definitely not edge on like this. This is what they're saying. Whereas this picture would suggest that actually if you feed black holes by infalling clouds, then if these infalling clouds form heavy enough accretion disks, there should be some preference for these accretion disks to be correlating with the cluster. So my expectation would be that in fact the spin of Sagittarius A star should be perpendicular to the galaxy. And the fact that you see Fermi bubbles which are perfectly aligned with the axis of the galaxy, to me, it's an argument in favor, at least, the fact that maybe Sagittarius star is rotating, in the same direction and the same axis as the galaxy. Okay, now just show you some pictures of other nuclear star clusters in order to show that they're rotating. This is the Milky Way. I already showed you some version of this. This is the edge-on galaxy, edge-on spiral galaxy. You see very strong rotation, quite a bit larger nuclear star cluster, but no jet. Okay, so you can't check whether the jet is aligned with the rotation of that cluster or not. This is an elliptical galaxy, I believe, with a quite complex pattern. You see some blue.
I'm sorry, Yuri. What is the point here that nuclear star clusters are rotating?
Rotating, yes.
Okay.
This is the point. I was just, because I'm not an observer, I don't know these observations very well. For me, it was important to go on internet and to look for observations, existing observations of rotating star clusters. I was assuming it would be important for you as well, given the story that I told. So I'm just showing you that they are rotating. This rotation is
all of them, or you can find those?
I can find examples that are developed. Look, Milky Way is rotating, NGC 4244 is rotating. These two are spiral galaxies. Okay, this is an elliptical galaxy or lenticular, but it basically doesn't have any well-defined overall sense of.
Sorry, perhaps I'm not formulating the question clearly. Is it how to say it? Is it always rotating, or is it just occasionally rotating?
How many examples of galaxies did you have
I
to
have
look at
found
before
4.
you found those?
One of them seems to be quite irregular. I can't say whether this is rotating or not.
Still, there is this, no?
Where?
Blue, yellow.
Which way?
From left corner to.
Well, this is red here and blue here, but if you look closer, it's blue here and red here. So, in fact, the authors of this paper say that the inner parts are counter-rotating relative to the outer parts. Okay, so this is how observers look at this data, and this is what they say. They see this like fine features. Whereas here, for example, it's also elliptical. This is elliptical galaxy or bulgy. This is elliptical galaxy, so it's not spiral. And still you see strong rotation. This is interesting example because here the nuclear star cluster is rotating like this. But if you go a little bit further, you have the inner edge of the disk of the galaxy. There is some disky part of this galaxy, and it's oriented completely different from this nuclear star cluster. So, you know, this are kinematically decoupled. This
R sub E that's written at the top is the physical radius of the white circle.
This is the physical radius of what observers think. Yes, that's right.
Of the white circle.
That's right.
There.
That's right. Okay, so now I'm really at the end. Rotating, I hope that what I try to convince you. Rotating clusters are centrifuges in the sense that the heavy objects are pushed out equatorially, except for they can't, of course, change their CMA axis in this formula, but they try to align as much as possible and to become as circular as possible, you know, in response to the rotation of the cluster. Then galactic center stellar disk. I hope this is the end of the puzzle. I hope the puzzle is resolved. And there is no need, you know, people were coming up with crazy ideas for what could be the source of this.
Intermediate mass black holes.
Yeah, people would say intermediate mass black holes coming in, wreaking havoc. People, including myself, I'm ashamed to say, you know, would come up with crazy. Huh?
It's not impossible.
It's not impossible, but you know, I don't think it's needed. I think, you know, based on what we know, there are more reasonable explanations. And I think there is a question of black hole spins, you know, Amry's, many interesting open questions. I hope I have made you at least a little bit as excited about this as I am myself. Okay, that's it.
Can you go back to your torque picture?
Which picture?
This one. So why would, when you disrupt the cluster, why would the mass be distributed such that your torque is preferentially towards the elements of the cluster? So 3 to 4.
Yeah.
Why wouldn't the distorted cluster be, I guess, randomly distributed?
Yeah, that's a very good question. I don't have a detailed answer. You know, I don't understand exactly how this distortion appears. In numerical experiments, this is what I see, because this is what happens. And thermodynamic argument that I gave tells you that this is what should happen, okay? But how exactly this is, you know, the mechanism, exactly how this distortion arises and why it's like that, I don't have a good answer. Maybe you can find an answer.
Do you have other questions for you?
How long does it take in your numerical simulations for them to align?
Well, you can see the scales.
Oh, right.
Those are mega years.
So this is semi-realistic for the Sagittarius.
Yeah. I took the best numbers I could find.
And what is the actual age of your stars?
They say 6 million years. Plus or minus.
So even the time scales do work.
Yeah.
Very suspicious.
So is there something that this predicts, like if you had LISA results and you found extreme mass ratio in spirals in galaxies with rotating nuclear star clusters and without, you'd see a difference? Is there Or you would see them in one but not in the other? Like, is there a prediction like
that's
that?
a great thing. That's a great question. I suspect, I don't have a formal argument, but my intuition tells me that if the nuclear star cluster is rotating and all of these things are operating, then the inspirals will be basically prograde and equatorial. Most of the inspirals will be prograde and equatorial. That nuclear star cluster will arrange things in such a way.
I see. And then if it's not rotating, then it's coming
It
in
could be more
randomly.
stochastic.
I see.
Isn't a kind of implicit in this that almost all galaxies would have the nuclear star cluster that was rotating with the?
So I don't know enough about this. It sounds like.
Because they will have had a gas
sounds like
experience sometime.
It sounds
and
like
they will
it,
have
yes.
and maybe the stars
Now,
will have
I
already
have to say
turned
that
as well.
people who study these nuclear star clusters, I'm learning that they're arguing with each other about how to form them. And some people think that these nuclear star clusters are formed by inspirals of old globular clusters, just old globular clusters feeling dynamical friction from the galaxy, spiraling towards the center and being tidally disrupted and joining this kind of cloud of stars. Or people think that this type of process that I've shown here, falling clouds, that the cluster can be also built up in this way, that clouds fall in, disrupt, form stars, and that we could build up some of these nuclear star clusters by this process. And there are people making arguments either way, and I think most people believe that both of these processes are at play in forming this nuclear star clusters. But I don't think it's known, for example, I had a letter from a colleague, Rainer Schoedel, who is one of the people who are studying this nuclear star clusters, and he said in his email that we don't really know what forms first, whether black holes form first or
What forms what? Oh, first.
Whether black holes form first or nuclear star clusters form first. So this is not known to us.
But when you speak of black holes in that context, you mean stellar mass?
No. I mean
The supermassive.
supermassive black holes.
So that's saying that the nuclear star clusters might be extremely old, since the supermassive black holes have been around
Yeah,
the ages of the galaxy.
that's right. So we don't know which came first and how exactly these two things are related. Sometimes you see nuclear star clusters without a supermassive black hole. Sometimes you see supermassive black holes which don't seem to have much of a star cluster around them. And oftentimes they're combined. So I think there is quite a bit of, if you want to extend this picture into the overall global picture of how things work in the whole universe, I think this becomes complicated. I mean, luckily, we have good examples near us. We have the Milky Way, we have Andromeda. Andromeda will be very different from the Milky Way because Andromeda has undergone this phase transition or whatever. It looks very lopsided. In fact, Andrei, in some of his configurations that he found, they look exactly like Andromeda disk, but very lopsided and with some rotations.
Any other questions?
Yes.
For this infalling cloud, is there, have you calculated the minimum mass it would need to be to produce this effect?
Yes, I have an analytical estimate, right? I have an analytical estimate for the timescale for this dynamical friction. I'm not 100% happy with this analytical estimate, but nonetheless it agrees roughly with numerical experiments that I have. And this estimate says that the timescale should be inversely proportional to the mass of the heavy object. Well, you saw the timescales. The mass in the stellar disk, which was doing this, was 8,000 solar masses, right? So if you drop a cloud which is 10,000 solar masses, it will take several mega years in a Milky Way type cluster to reorient itself in this way. If it's 10 to the 5, it's shorter. If it's 10 to the 3, it's longer.
All right, let's thank Yuri again. I'm going to stop the recording, and then probably people are going to keep asking questions. At least I am.
So how seriously do you take this tension with EHT?